Eva to record. I see she started. We are about 100 in class. Let us start. Speaking of attendance, I just want to remind you that Zoom is collecting attendance, so you know. Okay. So good afternoon again. Let me start the class. Let me put it on.
Professor?
Question?
Yes, I have a question concerning the homework.
Yes.
Yeah, I'm stuck on number 4. I'm not sure how to go about it.
Which homework? Homework number 4 or problem number 4?
Homework, the one that's due Thursday, that's number 4, right? Yeah, homework 4, number 4.
Problem number 4. Oh, okay. So this is, I think it's trigonometrical thing. All right, let me share that with you. Okay. There is that. So, can you see the cursor?
Yeah, we can see it. Do you mind zooming in for us?
That's the problem you're asking about?
Yes.
So what it is, it's turning. Let me see if I remember all the solutions. We have width, length. Oh, okay, it's given. Okay, so what it is, it's this distance is given. So we have a triangle with a right angle here. Okay, therefore you are able to figure out what is the centroid of the area or the volume. And then you can figure out how much is the volume. So buoyancy will be that force. You know where it is. The CG is exactly the center of that configuration. Therefore, you know what is the moment. Okay?
Yeah.
All right?
And then we just plug it in those equations that are displayed.
And it just, it actually serves to demonstrate how the center of buoyancy moves from the middle suddenly to the right. Therefore, I think this object is stable. Okay?
Okay.
All right, let's stop this one. And can we move on? We start? Okay, so I'll start, let's see, let me this one. All right, so I just remind you that we are now class 11, which is week number 6. So before you know, it's end of semester. Okay. Let's start. Already, let's see how many we have. We have almost 110, so it's pretty good. So we can really start with quorum. We developed the equations, and then we moved to hydrostatic for the pressure, and then we got back to the integral formulation for the one-dimensional flow. We added the Bernoulli equation, which is good for frictionless flow. And then we've seen that people like that kind of model, and then many instruments, even if there's light friction, are based on that principle. Pitot tube, Venturi tube, orifice, even injectors could be modeled with this type of approach. Then we started actually viscous flows. I'll repeat a little bit what we've done very quickly. And in the past, those models were developed sometimes before even the full equations were completely clarified. And they were referred to as exact solution because they thought that the formulation of the problem is exact, therefore the solution is exact, and now they refer that to exact solution for Navier-Stokes equations. Then just to confuse you a little bit, I told you that, hey, the Bernoulli is not going to work in this case, although there is a velocity distribution between the two plates, the two parallel plates, which are moving. And the velocity, of course, is changing if one of them is moving the fluid, but then the pressure is the same vertically. So you cannot use Bernoulli. And this is an example where it's not working because the friction is responsible for the whole flow. Okay, now here I just put here a reminder, and I just want to explain here. This is basically the rationale of the course, the way we run this course. So hopefully at this point, it's the first time I can actually shed some light of why we're doing things the way we are. So we looked at the equation momentum, and it shows that, like Newton said, acceleration equal to sigma f. And we looked at the forces, we said body force, but we call gravity basically, that's the only one we're dealing with. And there are pressure, which act on the surface. And then there are viscosity forces. So then we really played with the body force in the case and pressure, in the case of hydrostatics. We looked at center of pressure and things like that. And now it's the first time we're going to look more carefully into the viscous flow. So one more time, we tried to clarify a little bit acceleration before. We did a little bit of body force. We studied the rho G effect. And then we looked at the pressure, particularly how integrating the pressure gives us the center of pressure where the resultant is acting. And then now let's focus on viscosity. Viscosity, because before we said for the Bernoulli, there is no viscosity. So that's the whole chapter is about that. But then the important part is actually the pipe flow. Later on, we're going to see that the pipe flow was developed experimentally. And amazingly, it is exactly the same that we're going to arrive at using our formulations. Okay, so that's just the beginning. So now what I'm going to do is just very quickly go over. So what we did so far. So we tried to do the laminar flow between two plates. And let me get the pen. So this is the picture. When we started the semester, I had this case when the upper plate moves, lower place is stationary, and we developed a linear velocity distribution. I call that a shear flow. Okay. The one we're doing now, actually a bit more generic because it also has pressure distribution or gradient. So why would the flow move between those two plates? Option one is that the upper plate moves and the lower one is stationary, and therefore the upper, because of the no slip boundary condition, it kind of pulls the particles in the fluid with the surface. That's the linear case, this one. The other reason is that, say, none of the plates are moving, but there is a high pressure on the left-hand side and there's low pressure on the right-hand side. So the fluid is being moved. And your toothpaste, that's how you push high pressure one side, the toothpaste come out of the other side. Same way. So that's the same model. So Mr. Couette, a French gentleman, over 100 years ago, he developed these formulas, and I'm pretty much sure that he never looked at the Navier-Stokes equations because I think they weren't very clear those days. Anyway, so we started looking at the continuity equation right here, and we said that, okay, in this case, the flow goes only to the x direction, not sidewall flow and no lateral flow. Therefore, we ended up only with this term, which is right here. And therefore, we concluded that if there is any velocity distribution, it must be a function of z, which is depicted here. Okay, just pay attention to the coordinate system. We put the coordinate system at the base where the lower plate is not moving. Okay, I think most books will use the same nomenclature, but I'm pointing this out because later on we're going to use the flow in a circular pipe. And it's going to be exactly the same method, of course, cylindrical coordinates, but then we're going to place the coordinate system at the center. And that is actually going to be a more elegant solution. So I'm still repeating what we have done last time. So that was the continuity equation. Then we move to the momentum. So here is the incompressible steady state. I know you love that, but it all the assumption that there is no velocity to this direction, no velocity to this direction. So we ended up only with the pressure equals 0, or the pressure gradient. So the pressure must be constant to the y and z direction. And only some terms from that equation remain. And then the right-hand side term is z, related to z, and this one's related to x. So we conclude that because the flow is continuous and it's happening everywhere, this must be a constant. This must be a constant. So the pressure gradient along the is kind of a straight line. So this is dp dx. dp dx, and actually we can use ordinary differentials. So the pressure varies only with x, and that's it. So we concluded, which is very logical, mathematical thing. We're not wasting too much. Then we integrated that expression twice, and we ended up with a velocity distribution. Not very difficult, straightforward, high school stuff. We ended up with this. If you put the z over h here and make this one z squared over h squared, very clearly that term is a parabola. And this term is the shear flow that we studied at the beginning of the semester. So in this case, the flow moves because of the upper surface motion. In this case, the flow moves because of the pressure. Of course, there could be a combination of both, and then that's why we have here. The minus sign is a result of dp dx. If you remember, if you want the flow to move this direction, the x direction, then the pressure has to go down. High pressure on the left, low on the right, dp dx negative. So this term is negative, therefore we need the minus sign here. Okay, just, and then I showed the combination of the two flows. This is a combination of the two flows. Schematically, this would be the clear shear flow. This is when pressure is 0. Pressure is negative, pushing to the right, so it's a combination of the two. If the pressure is pushing to the left, there could be a reverse flow. So if I'm looking at this flow here, then actually the velocity gradient is backward here. And this one is forward. So this is also a possibility. So what we have here is we have this. We have a flow. I'm just trying to save here some space. The flow goes backwards, and now suddenly I start moving this to a velocity u, then this thing turns and moves here because of the upper plate is moving the upper layer. So we ended up here and here. Hopefully I'm explaining myself properly. Are you guys understand what I'm saying? Anybody wake up?
Yes.
Yeah, good, good, thank you. So that's what I'm saying. It's a combination of those two linear solutions. Everything is straightforward, very, very simple. Moving on. Then we try to put some more meaning into the term one-dimensional, two-dimensional. So we said that, okay, if suppose there's a flow, let's look at the one due to pressure distribution. Is there a flow like that? It's two-dimensional because this is z and this is x, and there is a variation of the velocity with z. If you want to use one velocity, u average, then we have to find out what is the average velocity and represent everything as a one-dimensional flow, which is typically what people do. It simplifies the whole process. And later on, we'll see that historically, that's how the formulation was developed. So we're saying that the two flows, the simple one is simply per unit width. Per unit width, the flow is going to be h, which is the spacing, times the average velocity. But in reality, the flow is not the average. We have to integrate the velocity where we found the velocity distribution. We have to integrate that. Therefore, the definition of average velocity is this, simply coming from here, straight coming from here. Then we went back to find out what is u, which was the previous slide. Okay, let me go, boop, boop, that. Remember that solution we had here? Same thing, we just copy that over there, and we just plug it in, which we did last time. So 1 over h into the integral dz from here, a polynomial, simple polynomial, this is it. And you solve it between h and 0, because you have to integrate all the way. And this is what we end up. So the average velocity is u hat, which is in the case of the shear flow. And this is in the case of the pressure, the flow due pressure. So one more time. This is this case. And the other one is this case. And of course, we already mentioned that it could be a combination of the two. The more important conclusion is what is the flow rate? Now again, this is kind of philosophical, infinite plates to left and right and moving, but still, if we take the two plates which are moving and then take a fixed width, it's a unit width, then we can say that the amount of fluid which is going through a section, a fixed section, let's say a z coordinate, is going to be this average velocity times h. Because remember, q is u and a. A represent the area. So the area is actually h times 1. So this is what we did, simply multiplied by h and h the third. So in the case of the velocity of the upper surface, that's it. So this is for the moving upper surface. And this is for the case when the fluid is moving because of the pressure. Now, this is a very interesting and important conclusion. It shows that if I change the pressure twice, the flow rate will increase twice. So the dependence on the pressure is linear. Let me just move forward super fast and just give you an example. I have a very long pipe and I'm transferring water, pumping water. And I have a pressure gradient, delta P. And as a result, I'm having a flow rate, which is Q. If I double 2, then the Q will double as well. So this is exactly the same result, which shows that before, it's not clear, but the flow rate is linearly linked to the pressure gradient. So that's a very important conclusion, which will pop up also in the case of the circular pipes. Okay, so that's what we did here. I believe this is where we stopped last time. So this would be new material, okay? So I would like to also find out what is the maximum velocity. So what we do is we take the derivative of that velocity distribution. Let me just go back here. Remember, that's the velocity distribution. I take the velocity, du dz, so it's going to be 1 over h, and then 1 over h, and 2 z over h, okay, whatever. Okay, so let's see. So that's what I did exactly. Here it is, right here. Now, we want to find some sort of a maximum, so we equate that to 0. Equate it to 0. And then we try to solve for the position. Okay, so let's solve for z over h. And we got this expression. So it's a bit tricky. I'm not sure if it's very elegant, but that's what we achieved. So now, if we have this case, then what would be the z? And remember, z goes, this is 0, goes here from 0 to z and to h. If I have a pure pressure-driven flow, then u is 0. Sorry. This is the case. Okay, wrong. I'm correcting myself. In this case, the maximum velocity here, because if you put dpt0 equals 0, that thing blows up, so it's not working. But in the case when u is equal 0, then we got half, which is this case, so this case is good. Okay, so this formula is not so great, but easy to remember. This is symmetric. The parabola is symmetric. The linear one is not, and it's obvious that the maximum velocity is at the plate, right? The velocity is there. Okay, so this was something which kind of, okay, I told you about it. I'm not super excited. Shear. Now this becomes important. So now, what is the shear in the fluid? In the fluid. So tau, remember, it's mu du dz. Oh, we did that here. We just did it here. So I just copy that over here. That's it. That's the shear. Now, you can look into that. And more interestingly is what happens to the shear at the upper surface and the lower surface. So if we go to the lower surface, we get this expression. Then we go to the upper surface, we get this expression. Let's look at that a bit closer. So in this case, it's du dz, and it's u over h, and it's a constant. So in this case, the shear is constant. This is tau. What is the shear means? That if I'm pulling this section, then the lower section is less. So du dz is positive. And we're looking at that expression here. Oh yeah, it is positive. So that's why if I put a coordinate system here, I end up with u over h. And of course, the shear is going to be mu times rho over h, which is right here. I don't have to recapture. Then in the case of this flow, it's a bit more tricky. There is a plus and there is a minus. So if I compare to that case, then the upper surface is pulling the lower one. Therefore, the shear is going to be positive here. If you look at the center of this thing, this expression, when z is equal h half, then this becomes 0. So it is going to look like that. So let me see if I was right. Yeah, on the lower surface, it's a minus sign, but remember dp dx is negative, therefore it is plus. And on the upper side, it's going to be minus. Am I convincing you?
Yeah, that sounds good.
Okay, convincing. Now, this one, I'm trying to convince you, but this one is not very elegant because in reality, because of the symmetry, it's exactly the same. But the reason is that we put the coordinate system here, and therefore we end up it being negative. So remember it that way. This is a problem with the coordinate system, but in reality, there is a symmetry upper and lower. Okay. Now we're moving on. And so this was just trying to show quantities. But in engineering, we really like to use non-dimensional numbers. The reason is that you can scale things up and down. And when we go through this chapter, you're gonna be very familiar with the approach, and you're also going to be clear why this is done. So one more time, using non-dimensional numbers allows you to scale the problem. You can do a little test with a tiny 2 little plates, and then you can extrapolate to some big surfaces in very similar condition using the non-dimensional number, which just ran away from me. Okay, so instead, and we already did that, instead of using shear, which represent friction, why don't we define a friction coefficient? Now, friction coefficient is, let's see, so the tau, the shear, is actually force per unit area. So it's like pressure. Now we go back to Mr. Bernoulli. So Mr. Bernoulli, even though he talked about flows without friction, he kind of created that quantity which is called the dynamic pressure. So this is also a pressure term. So typically in fluid mechanics, you try to normalize with a term like that. So the non-dimensional friction coefficient, which we call CF, is simply the shear, but normalized by a quantity, which is here the average velocity. So let's do it. Okay, so that's very interesting. So now let's try to do 2 examples. Repeat the one for the shear flow and one for the flow because of the pressure. Okay, so that's the only new element here. Okay, so let's go back to the first week of the semester. Shear flow. Nobody objected. I developed that and everything was good. So let's see. So now we have more knowledge, and we already claimed that in this case, pressure gradient is 0. The fluid moves because the upper surface moves at the capital velocity u. Therefore, the velocity distribution is linear. It's going to be u z over h. It's coming from the previous equation. Average velocity is at the center. I'm just repeating the previous formulas. You know what, if you don't trust me, here, okay, here we had the average velocity, remember u half, and then we had the shear later on. Okay, so I'm just repeating what we done over there. Okay, and now it's very obvious, very clear that, hey, it must be at the center. That's the average velocity. Flow rate, average velocity times h per unit width. Okay. Maximum velocity, remember the formula wasn't very friendly, but it's obvious that the velocity, maximum velocity is going to be at that point, which is the velocity of the plate. Shear force, mu u over h, we did at the beginning of the semester, which is a constant. So it's constant, the shear force is constant. Okay, that's it. And the friction coefficient. So tau, oh, we did tau here. Let me plug it in here. Dynamic pressure, average velocity. Average velocity I'm taking from here. Doing the algebra, that's it. Now, this is the first time that the Reynolds number pops up because of the algebra that we're doing with the fluid flow. Okay, so this is a very important moment. You guys should be really excited. I don't hear excitement now, but that's good, good. Thank you very much. Thank you. I have to cheer. Okay, so now we go to Mr. Reynolds, and 1842, 1912. He introduced, we'll go back to him in the future, and he introduced that quantity, which is a very important scaling factor in fluid mechanics. So what we're going to say that if the Reynolds number is the same, the flows are going to be similar. So I can take air with velocity and with some h and with mu, and then compare that to water, which is 1,000 times more, but I probably have to reduce the speed by 1,000. And also, but then actually it's a factor of 15 because mu is also being reduced. So density reduced, but it's a factor of 15. So if I want to do some testing, I have to have a scale of 15. Which direction the scale will learn that in a later chapter. We'll do that, but that's one of the many important aspects of that number. So if you write it down as a function of the Reynolds number, CF becomes a very simple thing. So you can look at the Reynolds number in this case as a non-dimensional velocity, like I tried to, because it's that here. So the friction coefficient is inversely related to the relative velocity. Okay, so non-dimensional, so the velocity goes up. It's not working well for me. Okay, I'm back here. Oh, I didn't select the pen. That's why I didn't like it. So here it is. We're going to see this trend. So if I plot here Reynolds, which is basically velocity, then the trend is negative. So typically the friction, the relative friction, not the absolute friction, will go down with velocity. That's very interesting. We'll see that later on when we start talking about experiments with pipe flow. Okay, so we did that one. That's the first time. Let's repeat the same thing. I think, I think we're gonna have a numerical example. Let's have a numerical, and then we repeat the same thing for the flow with pressure. All right, so let's see the numbers, how this thing looks like. So we have two plates moving at 5, that moves at 5 meters per second to the right. The lower is stationary. Clearance is 1 centimeter. This is meters second. And for example, we want to find out how much is the force in order to move the plate. So what we need to do, for example, just to copy, see what we have done so far. The average velocity is at the center, which is going to be 1/2 of the 5, 2.5. How much fluid goes through a section like that per unit width, per 1 meter? So it's going to be 0.01, which is the height, h. I just reversed that. 2.5, which is the average velocity. And then, I already did that and multiplied, so that's cubic meter per second, very small number. What is the maximum velocity on the upper surface? What is the shear? Mu, which is for water, about 0.01, 1,000. H, which is 1 centimeter, it's 1/100th of a meter. Velocity, so it's 0.5 Newton per meter square. It's not very large, but if you want to know how much force you need to add to that, that's the amount of force. So here it is, just for example, the force to pull 1 meter square is going to be 1 Newton. Okay, very, very simple. All right, let's do the same exercise for the flow due to the pressure.
Excuse me, Professor, could you go back to the last slide just a little bit more, please?
Yes.
Thank you.
You want to ask a question, or you just want to copy that or something?
I just wanted to copy it down right now, please.
Okay, sorry for moving fast. You guys can stop me anytime. Don't be shy.
I'm just a little slow right now.
Again, I mentioned that I asked the university to provide some tables that I can write, and then you can follow me faster. So far, nothing. And I realized that by doing the PowerPoint, I can move too fast for the class. So I'm trying to slow down, but if I'm too fast, please slow me down, okay?
Okay.
All right,
Thank you,
moving
Professor.
on. Same exercise. Okay, let me grab the pen. Okay, so it's the same formula for the velocity distribution. I just dropped the first term, which is the u half z over h or something like that. So I dropped that one. And so this is due to the pressure. I go back, if you look at the formula, the average velocity, we lost u half here. So that's the term that remains. Okay. One more time, average velocity versus pressure gradient. I was all excited about that, if you recall. So pressure, the flow rate is related directly to the pressure. Volumetric flow rate is the same per unit width. We just multiply by one more h, okay? And then there was the formula, which we didn't like very much, is where is the z over h? But then remember, turned out that if u is equal 0, the second term vanishes. So we ended up with z over h. So the maximum velocity is at the center. Okay, at the center. We go back to this formula and plug in z over h is equal h half. Okay, so it's going to be 1/2. It's going to be 1 minus 1, 1/2. So this is going to be it's 2, 2, 4, 8. So it's going to be u max equal 8. Now we're looking at the average velocity, and it turns out that the average velocity is here, 2/3. So this is the average velocity. Which is 2/3 of the maximum flow rate. Okay, very interesting conclusion. All right, I'm moving on. Now let's do the other thing. Let's do the shear. And again, if you remember, the shear was this. Okay, let me grab the pen. I'm just copying the same expression. If I'm going to plot that, I already plot that. I did this. The shear looked like this. Positive on the lower, 0 at the center, negative on the upper side. And then I plug in z equals 0, so I end up with a minus. And if I plug in z equal plus h, then I end up, I end up with a plus, yes. So it's positive on the plus, dpdh is negative, therefore this is negative, on the lower one is positive, as we discussed before. So this is the expression, and again, because of the coordinates, otherwise, everything would be plus. Okay, CF, it's tile. I just plug it this one here. We got this one, but this is not really very elegant expression. So we go back to the previous page where we showed that the average velocity is this. The reason is we have average velocity here. So let's see what is dpdx. Just resolve this dpdx and put it here. And it's just algebra, that's what it is. So now I go back to this equation here. H over half dp dx from here. Okay, it was a minus, minus goes away. Plug this one in here. This is coming from here. That's remained. Calculating. Reynolds number. Rho, we decided average velocity. H over mu as before. And here we go, 12 over Reynolds. Same trend. So if we call it a non-dimensional velocity, then Reynolds CF, it's going to be a slope like that. Same story, slightly different numbers. Also, pay attention that here we used your average velocity, and in the previous slides we used the actual velocity. Okay, so one more time. The Reynolds number is defined like that, but you can pick up H whatever you want, but usually you have to pick it wisely so it will be more representative of the problem. So anyway, I just want to point out that between these two cases, the definition of the Reynolds number is slightly different. Don't blame me, that's how it is. Okay. Okay, so basically at that point, I concluded the discussion on this. And the more important part, which is the flow through tubes, will come later. But I need to do some examples on this case and to strengthen our understanding, and also do some little juggling. So let's call the next two slides juggling, or trying to look at interesting stuff. So here is the flow due to pressure. Here's the flow due to pressure. Okay. So I'm trying to take a control volume from here to here. And now the control volume is in equilibrium. So probably it is pulling back the control volume by the force F here, because the shear pulls this way. So there is shear on the upper surface. And how much is the shear? Is tau times the area. What is the area? Is the length. So tau, F equal tau times area equal tau length and unit width. Okay, so that's what we're doing. So these are those two forces, F1 and F2, tau times the length per unit length. We take the results from the previous page, minus L over X. Forget minus plus, doesn't matter at this point. We just want it to be plus because dp dx is negative, multiplied by L. So we have F1 and F2, so basically we have to multiply this by 2, okay? And then what is the force that is pushing the control volume to this direction? It is the area, A, pushing this way, and the area is pushing the other way. But the pressure difference is delta P, so the force is going to be delta P times A. Okay, so what is the area? Is the length times H per unit width, okay? And then you plug in F1, F2, and F3, and everything is in equilibrium. So yeah, we did it right. It really complies with all the previous assumptions of control volume and equilibrium. Okay, that one. Let's do another one. Again, it's not super important, but just an interesting comparison between the two flows. Let me grab the pen. The flow due to pressure distribution or pressure gradient, and the shear flow. And we're trying to show two cases when the shear, I kind of missed the angle here. The shear angle is the same in both cases. So in the case of that case, that's very simple. We already said that the shear is constant. Now we need to figure out what is the shear on the wall, but we ended up with this expression. It's really not very user-friendly for that particular purpose, so we would like to resolve what is dp dx. Also, it would be nice to refer to maximum velocity, So that was the expression for maximum velocity. We solve this for dp dx, and we end up with this. And somehow the number is 4. So it turns out that the plate has to move 4 times faster than the maximum velocity due to the pressure gradient in order to have the same shear at the wall. Okay, anybody happy with that discovery? Happy students?
Sounds good.
Okay.
Sounds good, Professor.
I need happy students. Okay, good. Okay, moving on. So that's it. So now let's do examples. Okay, so let's do examples. And as usual, we go from simple to complicated. I think I did something very similar. So let's say 1 centimeter, this is water, 1,000 of Newton square meter square. Maximum velocity, okay, so we go just same formulation. So maximum velocity is 3.5 of, so it was U average was 2/3, so maximum velocity is 1.5 of the average velocity. Again, one more time, let me just get the pen. We're talking about, pen was not, okay, we're talking about this case. Okay, so the spacing is 1 centimeter, viscosity of water, calculate all those things that we did before. So if we have the maximum, the average velocity, remember it was 2/3, this is 1. Therefore, the maximum velocity is 1.5. Okay, we already developed the formula. Average velocity, so we find for dp dx, simply just taking the expression for the average velocity. Remember we said velocity versus pressure is linear. We take that formula, plug in the numbers, and just reverse dp dx, same formula. So it's going to be 12 space friction, mu, spacing, and velocity. It's 1 Newton, 1 Newton meter square per meter. Okay. Shear, just use the regular formula because you already have dp dx. So we just take this number, spacing half. There we go. Formula works. What is the Reynolds number? Rho, velocity, spacing, viscosity, 10 to the 4th. Friction coefficient, 1.2, 10 minus 10. So far, it means nothing to you, but later on, we're going to
Professor, you cut out for a bit.
just a second, let me just write it down and then I'll be responding. If it's less than 2,000, then the flow is laminar. Again, it's too early to discuss that, but I'm trying to. Okay, some student complained. I believe you complained about the internet.
Yes, sir.
Okay, it showed me that for a moment, we had some internet issues. Okay, should I repeat that or did I cover it properly?
Just to be safe, please.
Just to be safe. We have, so what we're doing, I'm just taking the formulas we developed, which is maximum velocity, average velocity, pressure gradient, shear, and the Reynolds number and friction. I just want to put numbers in it. So we're picking up a flow between a 1 centimeter spacing of 2 plates. And then we think that we would like to push water at an average velocity of 1.5 meters a second. So what is the maximum velocity? 1.5, because we mentioned that it's 2/3 of the maximum velocity. Then we're trying to find what's the pressure gradient. We have this formula, we plug it in here, just reverse it. Works. 120 Newton meter, which is pressure per meter. One is the shear. We just go back to the original definition because we already solved for the pressure gradient. Comes here, works. Reynolds number, we're doing that. Comes 10 to the 4th. Friction coefficient. Now, I mentioned that right now, these two numbers are kind of abstract. You say, okay, 10 to the 4th, who cares? But later on, we're going to learn that the nature of the flow, if it's laminar or turbulent, heavily depends on the Reynolds number. Where did I go? Here am I. So just remember that the Reynolds number is going to be very, very important. It's going to give the limit. In case of pipe flow, it's about 2,000. And then the friction coefficient, we'll see the numbers later on and you'll see if it's big or small. Okay, but right now that was kind of an algebraic example, see what kind of, how big are the quantities and how they look like. Okay, so we started with a simple problem. So what can the professor invent? That's usually what the students are asking. So here's one. Okay, so let's say that the upper, here's the picture. Let me get the pen. This was in an exam one day. Okay, it was in an exam a few years ago. So the upper plate is moving at a certain velocity, u, which is given 10 meters per second. And then we have, oh, this would be rho, okay. This is oil, rho. Okay, I'll check it in a minute. Because sometimes the word processor changes the things here. And that's mu. Okay, thank you very much, word processor. Okay, Microsoft, that's what Microsoft does to me. Anyway, so the upper surface moves, and then we would like to have zero shear on the upper surface. So most likely, we have to add some dp dx. So now, if you recall, we took the velocity distribution and multiplied by the derivative, mu, and this is what we found out. So just staying simply with math, we say, okay, we want this to be equal to 0. Okay, so then we have this expression. Okay, this is just algebra. We're trying to solve this. And we're trying to solve for how much is the pressure. And then turns out that this is just simple algebra. H is, this also becomes 2 over H. So it's 1, well, everything works out. And we end up with minus 2 mu over UH squared. Plug in the numbers, and it's coming minus 8, 10 minus 4 Newton meters per Newton meter. By the way, that's Pascal. I don't like that because it's a very small unit. But anyway, Newton meter square. And that's the pressure. So that's how much pressure we need in order to create this velocity. What is the average velocity? We take the formula now. Remember, we have the formula she developed. Plug in. This is for the shear flow. So what do we have? We have shear flow. And we have also pressure. So that's the combination of the two. That's what we got. And this is the quantity, simply just doing that. I'm just plugging in here the number. Turns out it's become 6, okay? So therefore 0.66 meters per second. Flow rate, simply multiply by H, which is 0.001. That's what it is. Shear. That's the shear. And now, what is on the upper surface and what is on the lower surface? This is the same thing we had here. Okay, and so on the lower surface, we're going to put H equals 0. H equals 0, and we end up with this number. That's on the lower surface. If you plug in H equal H, then it should end up being 0. Okay? I hope so. Okay, so you plug it in. This one, you do the algebra, comes out 0. On the lower surface, you plug in here h equals 0. So we have this. And we're going to go through the algebra. 2 mu u over. So it's twice as the u over h before. Okay? So that's just a little trick and not too complicated, just playing with the algebra. Okay, let's see. Let me just, for myself, okay, what is that? Oh, I have 2 more examples, 2 more examples. So again, what can the professor invent? Remember that I dropped the body force, the rho g term, because I said that we can replace that with gravity. So let's see the problem first. So we have, just a second, let me move that here. Okay, so parallel plates, assuming the oil density, again, this is rho, unfortunately, thanks Microsoft. And this is mu, Microsoft. And spacing is 1 centimeter. So imagine a 2-dimensional container. It's kind of a long one. And the spacing is 1 centimeter. It's full of liquid, which is oil. Viscosity is 0.3. It's SAE 30, basically. And what's the velocity profile? We know that now the velocity profile is probably going to be parabolic, like described here, like here. Okay, so it's going to be a velocity profile like this. So we need to do a whole bunch of calculations. And why is the flow moving? Because the pressure is changing with rho gh. So dp dx is rho gh. So it's negative to the z direction, minus z direction. And it's rho density times g. So this is the number. So then we have the equation, the average velocity. We developed this one. Okay. Develop that equation. I just plug in the numbers. We got 35 meters, so 25 centimeters, 0.25 meters per second. Maximum velocity is 2 thirds. So it's going to be, I put 75 actually. So my calculator is not super accurate. So this is 2 thirds. Okay. And okay, so that's maximum velocity. Flow rate, average velocity times h. This is per unit depth in this case. Unit depth. What is the shear on the wall? H half, 1 centimeter half. And then the pressure gradient, this one, we'll bring it in here. And it's 45 Newton per meter square, 45 pascals. Friction coefficient, very large. Okay, it's very viscous fluid. Okay, very viscous fluid. Okay, 12 over Reynolds number. Reynolds rho u average h over mu. So we put it up here, 156. How much is the Reynolds? 7.6. So the Reynolds is significantly below 2000. So we can conclude that the flow is laminar. Now, let me repeat that we called that chapter exact solutions. Some people claim that the term exact solutions are coming from this fact here, that for Reynolds number lower than 2000, these solutions will be exactly like the results from experiment. Okay? So what we're doing now is pretty accurate, pretty good. Okay? All right, we're getting close. Yeah, no, we have time, we have time. Mm-hmm. So this was kind of a quickie one, but if you have in front of you the slides, maybe 5 slides before, when I kind of listed all these quantities, all I did is just substituted the numerical values. So it was very straightforward. the only trick here is to understand that the pressure gradient is rho g. That's the PDX. And the PDX, and then we actually drop this term because we claim that they are exactly the same. All right. So another tricky question. Again, this is from an exam way back. So we have the velocity distribution. Okay, let me just get the time. We're talking about the flow due to pressure, the Hagen-Poiseuille flow. And we found out the velocity profile is this, which is depicted right here. This is the graphic. That formula is this picture. What is the average velocity? We've seen that this is the maximum velocity, and the average velocity is actually 2/3. So this is U average. U average right here. So here's that term. What we did not do is we tell you what is the coordinate Z over H for this position. And by the way, that repeats itself also here, Z over H. Correct? So how we solve that? What is that? Where is the velocity equal to the average velocity? Well, there's no rocket science here. This is the velocity distribution, and it must be equal to this term. No rocket science. Let's compare one to the other. And here we have an algebra where the only variable is Z over H. And of course, H over mu dp dx, I can cross out. Here I end up with 6, because it's 12 to 2. 6, Z over H squared. If I arrange it, I end up with a quadratic equation, high school stuff. You solve the high school thing, and you end up with 0.211. So this would be Z over H 0.211. And here it's 0.788. But this distance is also 0.211. So it's exactly the same thing, it's symmetric. So these are the coordinates in terms of Z for the average velocity. Okay. All right, so I believe that at this point we concluded that discussion about the parallel plates, and now we're getting more serious, and we're going to repeat the same exercise, exactly the same thing, for the flow in circular pipes or tubes or whatever. Any questions up to this point? Questions? One question, two questions. Can I continue?
Yes, Professor.
Yes.
Yeah, Professor.
Okay. All right. So we are towards the end. I have 8 minutes left or something. So we want to do the same thing. Okay. So it's not scary. It's a bit scary, but don't get scared. Okay. So let me go here. So we would like to do the same thing, but now for the flow in circular pipes. This is a really important problem, and students will use that. And turns out that some of the formulation we're going to do is very practical, actually working pretty well. It is called the Hagen-Poiseuille flow in circular pipes. And 19th century, it was Hagen in Germany and Mr. Poiseuille in France. Mr. Poiseuille was 2 years younger than Hagen. And I'm not sure if they ever met, but historically, we have quite often, like with the Navier and Stokes equations, that two people developing the same things and they don't talk to each other because there's no internet. Okay, and then even the mail didn't work. They used pigeons and stuff like that. So don't be amazed. We are in a different world now. So I mentioned that the math is very similar, but we need to now look at cylindrical coordinates. So it's going to be very, very similar, but the cylindrical coordinates. I know you love cylindrical coordinates, but I'm telling you it's going to be almost exactly. Almost exactly. Actually, it's going to be more elegant because we're going to pick the coordinate system at the center of the pipe. So now if I'm going to look at the shear, it's going to look like that. It's going to be positive both directions. Okay, so that kind of resembles the flow due to pressure. It's very similar. Anyway, so the downside is that we're going to use cylindrical coordinates. The positive side is that we're going to do a similar approach. And then I must say that we're going to assume that the flow is fully developed. So this is a long pipeline, and long pipelines exist all over the world. It's in your house, it's the water, it's everywhere. So we kind of neglecting the inflow condition, which is maybe a few diameters at the beginning. But we're looking at the fully developed flow. And then again, as before, we use the gravitation as the only body force. And now we're looking at the problem, and it's not too difficult to convince you that the flow goes only to the x direction. And perhaps the continuity equation will tell us that the velocity profile is a function of r. One more time, what is the coordinate system? The coordinate system is x is the length of the pipe. Instead of z, we're going to have r, which is the radial coordinate system. And then there's a tangential velocity. Again, this is in the coordinate system. So now it's really two-dimensional flow in the pipe, and the flow goes only to the x direction. So qx is not zero, but the others are zero, very, very simple. I have a few moments to scare you, and then we'll stop. Okay, so now I'm going to do the same thing as I did before. I'm going to show you the full equations, and then we just simplify them by this type of assumption. Okay, so we just simplify them. So let's jump into that. So I did not show it, but I mentioned that the coordinates actually in the book appear in, the Navier-Stokes equation appear in terms of the cylindrical coordinate. Here's the cylindrical coordinate at the bottom, which I mentioned. So again, now in our case, the pipe is going to be like that. It's going to go along here. So that's the pipe. My drawing is not super nice, but that's what something like this. Okay, so, and then this is the center. That's how it's going to go. We mentioned there is no tangential velocity, no radial velocity, velocity only in the direction. And this would be the continuity equation. But I'm looking at the continuity equation, no r direction, no theta direction, no r direction. So I end up with dqx equals 0, which means q of x is a constant, it's fixed. So dqx is constant. It's only a function of r, not x, it's a constant. Then I'm looking at the Navier-Stokes equation. This would be r direction, r, q theta, nothing, everything is 0. Theta direction, everything is this 0, but this term we cannot say. And here, this is again, this is the material derivative. And the next slide, I'm going to show that. We're running out of. Let me show the next slide. So let's just talk about what I just mentioned earlier verbally. The continuity equation is this, but then I claim that because we assume that the velocities are 0, okay, I got that. So this is 0, 0, 0 because of that argument. And therefore, this equation becomes that. So if q of x is constant, then the only variation is possible when it is a function of r, which is depicted here. Okay, so that's what's here. That's what it is. That's the only possibility. So now this was the continuity, and we have to move to the full Navier-Stokes. Okay, I just show it to you and I repeat it next time, just very quickly. So what we do with those equations very, very quickly, we have here the three, and I'll repeat it again, don't get, but just to conclude that here I have the three direction, but only that one is applicable. So all the x derivatives are basically going to be zero, because before we stated that dqx, dx also zero. So this goes away. We have no body force, and then we have to look at that one, which is this term. This is exactly this one, but we threw away the terms to the r and the theta direction. So to the r direction, this equation, theta direction, this equation, and this one is a bit more complicated to the x direction, but we'll end up with the same. This will tell us that the pressure is constant in the radial direction, very much like we had before. We had a flow like that, and we said the pressure is constant in a straight line. Tangentially, the same story, constant. This one, we have to integrate. It's an algebraic integration. We'll do that. We'll do it next time more carefully. And thank you for being so quiet. Hopefully I didn't put you to sleep. And I think the flow in pipes is going to be a very interesting topic, particularly for civil engineers. Then you have open channel flows, and basically they're all based on that formulation somehow. All right, any questions toward the end of the class? Let me just get out of this. Anybody listening?